Okay class, today our topic magnetic effect of currents, and in this today we are going to discuss the torque on a current loop placed in a magnetic field. Torque on current loop placed in a magnetic field. Current loop placed in a magnetic field. Now, in last topic, we have discussed that when a current carrying conductor is placed in a magnetic field, there will be a force on magnetic field, that is BIN sine theta, whose direction is given by Fleming left hand rule. Now we are considering a loop. Let me have the rectangular loop placed in a magnetic field. Placed in a magnetic field. Let it placed suspending position. Rectangular loop. The name of the loop is A, B, C, D. Rectangular loop. And this is the magnetic field direction. Magnetic field direction. B vector. Let the loop carry the current from A, B, C, D. This is the direction of the current. Rectangular coil A, B, C, D suspended in a uniform magnetic field B vector. This magnetic field is in plane of paper from left to right. And here AB and CD is the length of the coil ABCD, and AD BC is the breadth of the coil. Okay, and the current is flowing in ABCD direction. Now we have the two more terms here. In this we have two perpendiculars, XM and YN. Two perpendiculars on the or normals to the plane of the coil, XM and the YN. XM or YN. These are the two perpendiculars on this loop, normals. Now we have this angle between this perpendicular and magnetic field is theta, and this is perpendicular, so this angle is 90 degree. Similarly, here the angle between this perpendicular and magnetic field is theta, and this angle is 90 degree. Okay. Now we have studied that when a current carrying length or conductor is placed in a magnetic field, it experiences the force. So each side of the coil experiences the force. We can say F1 vector, F2 vector, F3 vector, F4 vector are the forces along the length of this four current carrying sides DA, AB, BC, CD. So first we say that arm DA. Now this force is F. Let's take the magnitude of this force. And what's the current element? Current, length, dA, magnitude, B vector. Now what's the direction between them? What's the direction? B vector and current direction. Current element direction is 90 plus theta. So sine 90 plus theta, and we got B, this length BL. This is the length AD is breadth, BB cos theta, current IBB cos theta, and this is in the plane of coil and upward. How we get this direction? That is in upward direction by using this Fleming left hand rule. This is the direction, plane in the plane of paper towards this left, and this is the current direction. So this is the force direction, that is the F1 direction. Now come to this point BC, that is arm BC. F1 force, F2 forces, current, magnetic field, again breadth, but the sign is now this is the direction and this angle become 90 minus theta. Then again it is BIB cos theta. But now with the change of current direction, force will be become downward. This is the magnetic field, current, and force will be downward direction. That is F2 vector. Now these two forces have same line of action, so they cancel out. So in this rectangular coil, when it is suspended in a magnetic field, these two forces along the breadth of the coil, they are equal and opposite, so they cancel out each other. Now on the arm, this arm that is on AB, now F3 force, this is F3 vector force. Now they are perpendicular, magnetic field, current direction, this is the force. And similarly, magnetic field, current direction, and this is the force F4 vector. Here the angle is 90 degree. So this is BIL sine 90 degree. And F4 is BIL sine 90 degree. These forces are BIL and they are perpendicular to the plane of paper. Now these forces have the same line of action, but these have the different line of action with a perpendicular distance. So these two forces will give a torque on the coil that will be constitute the torque on coil. So what's the result? When the current carrying coil is placed or suspended in a magnetic field, it experiences a torque. And how we calculate this torque? How we calculate this torque? Let's draw this simplified diagram. Simplified diagram means we have considered only AD side. AD, top of the coil when we view from the top side. Now this is F3 and this is the force F4. These two forces constitute the torque. Now this is the magnetic field B vector, or we can say this is the perpendicular YN or XM, whatever you know, because in notes we write it YN, that is the perpendicular. Now this is the direction, perpendicular and magnetic field direction is angle is theta, and this is the plane of the coil and magnetic field and angle is alpha. So remember this, the angle between normal to the plane of coil and magnetic field is theta, and the angle between plane of coil and magnetic field is alpha. Now these two forces which are equal and opposite, they constitute the torque, and this is the perpendicular distance between them, that is called this KD distance. And how we calculate this? This is theta and the perpendicular distance calculate as sine theta, that is KD upon AD, or KD is AD sine theta, or KD is B sine theta. This is the perpendicular distance. Now the torque is either force, that is BIL, these F3, F4 is BIL, and the perpendicular distance B sine theta, length into breadth is called BIA sine theta. BIA sine theta. This is a vector quantity. So how we write the vector quantity? Cross product current and B vector. So what is the torque? And this is the dipole moment, the magnetic moment for a current loop, that is M vector. So torque is M vector cross B vector, or MB sine theta. Means you write the torque MB sine theta when theta is the angle between perpendicular to the plane of coil and magnetic field. But if we consider this alpha, means if there is some situation or some problem where the angle is considered plane of the coil and magnetic field, that is theta plus alpha is 90 degree. and alpha is 90 minus theta. We consider that alpha is 90 minus theta or theta is 90 minus alpha. So sine theta, sine 90 minus alpha is cos alpha. Means torque can be written as mb cos alpha when we considering that the angle between the plane of the coil and magnetic field. So this thing is remember in this topic. And if we have the number of turns, we're considering that number of turns, that is equal to n. We can write the n here also. We can write the n here also. That is the number of turns. And this we drive it for the rectangular loop, but we can use this on any planar current loop of any shape that is suspended in a magnetic field. So when a current carrying coil is suspended in a magnetic field, it experiences the torque, that is mb sine theta, or we can say BIA sine theta, where theta is the angle between normal to the plane of coil and magnetic field. And if we are considering the angle between plane of coil and magnetic field, then we consider it as a alpha. And this is the base of moving coil galvanometer, means the device which is used to measure the current, very sensitive device called moving coil galvanometer, and it is based on this. When a current carrying loop is placed in a magnetic field, it experiences a torque, and that is a moving coil galvanometer. Very important topic in 12th class, moving coil galvanometer, and its principle is the coil placed in a magnetic field experience a torque. Now what's the construction? Simple guidelines of the construction. There is a rectangular coil having the number of turns, rectangular coil, soft iron core of the coil. One side of the coil is with the suspension wire and torsion head. Suspension wire is made of special material, phosphorus bronze, that we have explained later in this experiment, in this article, that why the phosphorus bronze wire is used as a suspension coil. And this is the spring, second end is attached to the spring. And here the concave base, two poles of the electromagnet north south to provide the magnetic field. This is the torsion head, and there is a small mirror fixed on the suspension wire to see the twisting or to see the reading of the devices. But now the modified devices, they don't have this such type of mirror. They just only have the scale on the top and a pointer which gives the value of the current, and the whole apparatus that is fixed, enclosed to avoid any disturbance. There the leveling screw, so that the coil easily twist, don't touch the values, and we have the terminals across which we connect. By using these, we connect this device in the circuit. These are, one is connected to with this, and the second one is connected to this, so that the twisting must be properly. Okay, so these are the basic form of the moving coil galvanometer. Rectangular coil, soft iron core, concave based pole, electromagnets, suspension wire, phosphorus bronze. One is the torsion head, second with the spring, leveling screw, and the terminals. Now its theories again. When the current is passed, this is a rectangular coil, and this side forces are balanced, same last article, and these two forces, they constituted torque which twist the coil. Means the two forces and a number of turns, and the two forces on the arm AB and CD, that will be AB or CD, that is number of turns BIL. Now this is the total force. Outward, normally outward, on this outward force is acting, outward, and on CD inward force is acting, which constitute the torque. Now this torque, it deflect the coil. Coil deflect. This is called deflecting torque, which so the coil gets twisted and the suspension wire gets twisted, so that when the coil is deflecting torque, suspension wire gets twisted, it again create a restoring force which make it to move in its original position. And when the both deflecting torque and restoring torque become equal, then it gives the particular measurement of particular direction, particular current. So at the equilibrium, deflecting torque and restoring torque means in moving coil galvanometer, when the current passed through the coil of the galvanometer, the two forces that will along its two sides will constitute a torque, and that torque give the twist in the suspension wire, and in suspension wire material create the restoring torque. And the equilibrium, when the deflecting and restoring torque become equal, that will be give the value of the current. Now first we have deflecting torque. How we get this deflecting torque? Now at any position, north, south, and again we have this coil side, again same to give the torque. This is perpendicular, this is magnetic field, and again here we have the direction theta and here we have the direction alpha, because here we say that the angle is alpha, and this is the perpendicular distance again, KD. Now this is alpha, and AD is equal to breadth of the coil, B cos alpha. Now this is the force, and the deflecting torque is equal to either force into perpendicular distance, and length of breadth become area of the coil, that is NBIA cos alpha. Now the suspension wire is a special material, and if K is the restoring torque per unit twist for the material of suspension wire, K is the restoring torque, then restoring torque means K alpha, and at equilibrium N by A cos alpha is K alpha, and we have to measure the current. So what we write here, K NBA alpha upon cos alpha. But for a given galvanometer, these factors are constant: suspension wire, number of turns, magnetic field, area. So current become proportional to alpha upon cos alpha. But here the current is not directly proportional to the deflection of the coil to get the linear reading. So there is some modification is required, and that modification means the concave poles. We draw in construction that two concave poles are required to give the magnetic field for the coil of the galvanometer. This concave pole produce the radial magnetic field towards the center, radial center magnetic field, and in this magnetic field the plane of the coil, this one plane of the coil is always parallel to the magnetic field at the all positions, parallel to the magnetic field, and the perpendicular distance parallel to the magnetic field. This is coil, this is magnetic field, and in this coil is always parallel to this magnetic field, means here the perpendicular distance is always B, means this is the radial magnetic field, and when the perpendicular distance is always B, we don't have the cos alpha here, and the current become proportional to the deflection produced in the coil, and the linear scale is used here. So here we have a factors that what is the purpose of this concave poles. They produce the radial magnetic field. And what is the use of this radial magnetic field? The plane of the coil become parallel to the magnetic field at the all situations. So here this is called the galvanometer constant G, and the current is proportional to the alpha. So this is all about moving coil galvanometer. Torque depends and this deflection. Now we have the two main factors, sensitivity of galvanometer, and the sensitivity of galvanometer is in two forms, current sensitivity and the voltage sensitivity. Current sensitivity that is equal to alpha upon I. Same, the last one, that is NBA upon K. And the voltage sensitivity is alpha upon B, alpha upon IR, or we can say NBA upon KR, where R is the resistance of the coil, that is the sensitivity. So it is more sensitive, it gives the deflection for the small current. Means how we define current sensitivity? The deflection produced in the galvanometer coil passing unit current through it. And voltage sensitivity, deflection produced in the galvanometer when the unit voltage is applied across the coil. So mathematically this is current sensitivity and this is the voltage sensitivity. So this current, to become it more sensitive, this value should be increased. But number of turns and area, that will be increased in a limited amount, because if number of turns increases, length of the coil increases, that will be increased the resistance. And if area is increased beyond the limits, then the device becomes bulky and it is not convenient to use the galvanometer. So these two, N and A, they should increase in a limited form. So we increase this B and K. So magnetic field, we use a strong concave pole electromagnets, and for this to decreasing this K, the suspension wire is made of phosphorus bronze material, for which the K is small and galvanometer is more sensitive. And to make it more sensitive, this suspension wire may be in the form of a strip, and that strip will increase the sensitivity of the galvanometer. Now, galvanometer is not directly used in place of ammeter. Ammeter is also a device which is used to measure the current, but the galvanometer is not directly used because it is not to use the measure the large current. If the large current passes through its coil, it damages the coil. Heat up current, ज़्यादा heat produce करदा, that will damage the coil. So, and there is a one difference. Galvanometer used to measure the current, ammeter used to measure the current, and voltmeter used to measure the voltage. But some modification, galvanometer is used to measure the both current and voltage in place of ammeter and voltmeter. In galvanometer, the zero is between the scales. Means galvanometer ਦੇ pointer ਇੱਥੇ ਹੁੰਦਾ ਤੇ ਦੋਨੋਂ ਪਾਸੇ move ਕਰ ਸਕਦਾ, but ammeter ਦੇ ਵਿੱਚ pointer 0 ਤੋਂ ਸਿਰਫ ਇੱਕ side ਤੇ move ਕਰਦਾ, voltmeter ਚ ਵੀ ਇੱਕ side ਤੇ move ਕਰਦਾ. This is the basic difference that can be clear in the laboratory form. So we have to convert the galvanometer into ammeter. Now how we convert the galvanometer into ammeter? This is the galvanometer. Here we have a small resistance. This is called shunt. Again, this is not a special resistance. It is a small resistance connected always in parallel. And this parallel combination is treated as a ammeter. This is the current. This is Ig. And this is I minus Ig. Now what is this Ig? The current, maximum current passing through the galvanometer which gives the full scale deflection is called Ig. So they are in parallel. So I minus Ig, S is Ig, G means resistance of galvanometer. So this shunt resistance you can calculate. Means if you have the galvanometer resistance, current, and for which you have to convert it range, and this must be greater than from this. मतलब जे IG ਦੀ value 2 milliampere है तो I ਦੀ value 5 एम्पीयर तक भी हो सकती है. So we have to calculate this shunt resistance जो हमेशा parallel लगाना galvanometer दे, but this ammeter is connected in a series because it is the resistance of the ammeter is small, so it is always connected in series to find the to measure the current of the device. And how we convert it into the voltmeter? Voltmeter convert currently galvanometer, and there is a parallel resistance R, and this both will be act as a voltmeter. And here we have the IG current, okay? Then here, but we consider this is in series, so current is voltage upon the current is this voltage upon R plus resistance G. So R plus G V upon IG, and this R is V upon IG minus G. So these two terms are very important. How we convert the galvanometer into ammeter and how we convert the galvanometer into voltmeter. Here we require the shunt resistance that should be connected in parallel to galvanometer, but the combination is connected in series, and the ammeter that has the minimum resistance, or ideal ammeter has a zero resistance, and it is ammeter is always connected in a series, but the voltmeter we have to connect the resistance in series to galvanometer, but this combination is as a voltmeter and it is always connected in a parallel, and we require this resistance. So this is the conversion of this galvanometer into ammeter and voltmeter. Okay, thank you.